Um, I would like to ask some Italian guys. So it's easy because they're both Andreas. So we have Mr. Andrea BRASCHI and Mr. Andrea CONTINELLA. So they made this thesis in Politecnico di Milano. And actually, they tried to observe the behavior of Trojans and with combination memory forensic inspections, especially on Trojans that are for banking. So, welcome. Let's start one. So they will share the presentation, yeah?
Yeah.
Okay,
Yeah.
so one can sit and all can continue. Thank you. Okay.
Okay, I am Andrea CONTINELLA, and so we will talk about banking Trojans, and that can be also called information stealers. What are information stealers? A particular kind of malware that aim at stealing credentials such as username and passwords. They are also known as banking Trojans because they often target banking credentials to perform online financial frauds. There are different, many families of this malware. The most famous are Zeus, SpyEye, and Citadel. What they do, basically, they are able to intercept all the data that users, victims, submit into web forms. And they can also steal files, hijack browser session, and use the victim's device as a proxy. Why do we care about this malware? Well, of course, they are dangerous because they directly affect the victim's finances, and they are the main cause of billions of dollars stolen by cyber criminals in the last years. And furthermore, this malware is constantly updated and maintained by cyber criminals in order to evade the modern defense mechanism. And maybe the most scary thing is that this malware is sold in toolkit on the underground markets. So anyone, independently from their skills, can buy such kit that contains administration panels, instructions, configuration files. So anyone can build and create this customized sample. So this led to a huge number of different samples and to a low detection rate by antiviruses. And these charts show the number of computers infected by banking Trojans in the last year. And just to give you an example of some months ago, the FBI announced a reward up to $3 million for information leading to the arrest of this man that was responsible for having managed a Game Over Zeus botnet and stolen more than $1 million. So how this malware work? Basically, they perform an attack called main the browser that exploit API hooking techniques to be able to intercept all the data that flow inside the browser. And another important feature of this malware is the web inject. That is a module that allows cybercriminals to silently modify web pages on the infected host. And this is used by cybercriminals to add further fields in forms, and so to steal further sensitive information. You can see an example of, in this picture, of a login form that was rendered in a client and an infected machine. This instead is the scheme of the hooking mechanism that is used by this kind of malware. The main peculiarities of such approach is it works in user space, and doing so, the malware can get the data after they have been decrypted. So it is effective also in the case of an HTTPS connection. This instead is an example of a configuration file, because every web inject module relies on configuration files where attackers can define their own injections. And each injection is defined by 3 fields. The set URL define the URL or a regular expression that match more pages of a given domain. And this is the target of the injection. Then we have the data before that identify the position in the page where the new content is injected, and the data inject is the HTML or JavaScript content to be injected. The state of the art and of the detection of this malware have to face some limitations, some issues. First of all, malware executables are packed and obfuscated, so static analysis is difficult. Also, configuration files are encrypted and often embedded in the final executable. And there are many different families that target different browsers or use different API hooking methods. So the main limitations of antiviruses and other work is that they are strictly dependent on the specific implementation of the malware, and so they need to be a malware reverse engineering process is often needed to update the signatures. So our goal is to capture the behavior of these families and speed up the generation of signatures, but we want that these signatures are the more general as possible. So we want to minimize the reliance upon the implementation details, and we want to avoid any kind of manual reverse engineering. So the basic idea on which our system is based is the web page differential analysis. So we exploit the visible DOM modifications that the malware cause inside the HTML pages, and comparing DOM downloaded in clean machines with those downloaded in infected machine, we can extract these modifications and generate signatures. This approach has the main advantage to be general, so independent from the specific implementation, but it is not easy because not all the differences in web pages are malicious, since nowadays web pages are extremely dynamic. So we have the web page differential analysis that can allow us to generate signatures identifying the injection performed by the malware. To this approach, we combined memory forensic inspection to extract from the memory dump of an infected machine the web inject targets that are, as I said, the URL of the regular expression that describe the targets of the injections. And this information is really useful to understand what are the targets of the malware and to validate our signatures. So we designed and implemented Prometheus. This is the overview of a sample analysis performed by Prometheus that takes in input a sample and a list of URLs. We have the web page differential analysis and the memory analysis that are performed in parallel. For what about the web page differential analysis, in the first phase, we start a certain number of virtual machines, in fact, part of them with the malware to be analyzed, and download in each machine the DOMs of the list of URL that is given as an input. Then in the next phase, we use the collected DOMs that are marked as clean or infected, and we produce two lists of differences. The first list contains all the differences that are output by the comparison of two clean DOMs, so are the clean differences. And the second list contains the differences output by the comparison of a clean DOM and an infected DOM. Finally, in the last phase, we filter these differences in order to discard the legitimate ones and to obtain the real injection. And the real injections generate our signatures. For what about the memory analysis, we initially start another VM and in fact open the browser and we dump its memory. And we look inside the memory of the browsers for the strings that match the pseudo URL format of the web inject targets. Finally, we use the regular expression that describe the targets of the web inject to validate our signatures. So we check if any of the extracted regular expressions match any of the URLs that we processed. And this is an example of a regular expressions that is, in this case, the target of these injections. So I'll leave the words to my other colleague.
Hi, I'm Andrea BRASCHI, and I will go through the presentation. With our system, we extract the difference, as my colleague already said, and those differences are composed by three elements: the type of the modifications we find, so it can be a node insertion, a node modification, a node deletion, or something like that, and then the X path or the XML path at which the difference happened, and the content of the subject of the modifications. In order to, for the filtering phase that my colleague mentions, we implemented three heuristics. The first one is simply to remove all those differences that are harmless, so changing in style, reordering of node, all those differences that cannot be used by the by the attacker to steal some information. The second heuristics is to is to filter out all those differences that are generated from the comparison of two clean DOMs, because those differences are all those part of the page that are dynamically changed dynamically in the web page. So, for instance, a session ID or some advertising inside the page. The third heuristics assume that the model of our injection is static, so the attackers inject static content inside the web pages. So every malware, every virtual machine infected should manifest the same injection. So we keep all those different that are present in the majority of the infected virtual machine. Here there's an example of a signature extracted by our system. As you can see, there's a input field added in a form asking for a OTP password. Then for the evaluation phase, we evaluated Prometheus against a set of 196 samples Zeus, and however, of these, only 135 were active, and we tested those samples against 68 URLs of one banking website. Numbers are continuously evolving because we have implemented a crawler which crawls for malware from sites like Zeus Tracker or Spy Tracker, and so we are continuously analyzing new malware, and that's in order to evaluate the effectiveness of our tool, we measure the rate of false difference. False difference are all those differences which Prometheus detect as injection, but effectively are benign and benign difference inside the pages. As you can see, with 12 virtual machines, we have a rate of false difference which is of the 0.7%, and through the validation with the result from the memory forensic analysis, we reduced this rate to the 0.26%. For what concerns the memory forensic analysis, we extracted successfully from the sample analyzed 694 distinct regular expressions, and we found out that all the true injections are founded on URL matching some of the regular expressions founded in memory, but not all the regular expressions in memory are matching a URL with injection. This may also mean that malware producer or attacker not always are interested in injecting content and then asking additional information to the users, but sometimes they only look to grab the content that the user put in the form. This kind of observation could have not been founded only with the differential analysis, or comparing those two analyses, memory and differential, we can also observe this fact. For what concerns performance, as you may notice, with the increasing number of DOMs compared, and so virtual machine utilized, we have a slightly increase of the performance. However, on average, our system is able to analyze one URL in 6 seconds. What about limitations of our tools? Our tools is not able to detect those injections that perfectly overlap dynamically node inside the pages, for example, advertising or other dynamic node, but those injections are very hard to produce and not so useful for an attacker. Also, our system is not able to detect and analyze those malware which perform dynamic injection, so that inject different content at every download of a certain page, but also we haven't seen any of these malware so far. For what regards future works, one future work could be to implement a client-side protection and detection system with a proper signature matching algorithm in order to detect if a client is infected by a determined particular kind of malware effect, acting as a man in the browser. This system, our system, could also be used as to enhance the malware intelligence laboratory of banks and other systems targeted by those malwares, working as a backend sandbox to analyze founded malware, and also we could focus more on those corner cases pointed out during the limitations explanation. Then, coming to the conclusions, we have with this project we have shown a simple and effective technique to extract the web inject configuration file from malware acting as a man in the browser without the need of any reverse engineering for quite quickly and in a way that's pretty independent from the implementation of the malware analyzed and the technique used to behave like a man in the browser. That's all. Thank you. Thank you also to say fair question.
Thank you, both Andreas. Okay, so I don't know if we have a question for the World Committee.
Okay, well, it's my turn to start now. First of all, I think you took an interesting approach. It's good to look on the same thing from a different angle. Still, I would like to go a little bit on the limitations of the system. Do I get it right that you basically made a custom approach basically fitting only for Zeus? Or to which extent, I mean, you basically, your whole system you introduced is seems only fitting for Zeus malware family. Or have you, let's start vice versa. Have you tried your methodology and your system also for other malware using the same method, but is not Zeus?
Yeah, we performed some tests on a sample of Citadel and one of SpyEye, but we did not find an ample data set of other families that are active, because for our evaluation we needed the CNC server behind this Trojan has to be active, because this malware as soon as starts download by the CNC server the configuration file encrypted to perform the injection. So if the CNC server is not up, our malware will not manifest its behavior. So we test our approach on a customized sample of Citadel that we built, but we did not manage to find an ample data set of different families that are active.
Okay. Next question for understanding. As far as I understand the Zeus botnet or Zeus malware, the URLs are pre-configured when you buy the toolkit, and the owner of such a toolkit then can customize this configuration file, putting in his very own URLs he want to hijack or to monitor, and then pushing out the configuration file. So this configuration file normally is encrypted.
Yeah.
How do you get then the real which URLs you were looking for. I hope it was the ones in the encryption, in the encrypted configuration file, and if so, and how did you get them out?
Okay, we used as initial list for the URLs to be analyzed web inject configuration file that was leaked. So of course anyone can modify and add new URLs. Then from the memory analysis, as we said, we can get the regular expressions of the URLs, so of the target. And from this list of regular expression extracted from the memory forensic, we managed to add further URLs in our system to be analyzed.
Okay, that means that in general your system is only working if you can do the memory forensic. The memory forensic is
or if you submit also the URLs to be analyzed. Yeah, of course. The URLs are considered as an initial input of the system, and then can be updated performing the memory forensics.
For instance, if you're a bank administrator or CISO of a bank, you're interested in monitoring if there's some malware targeting certain page of your site. So you could provide to the tool those URL and monitor them with the tool.
Okay, it's understood. Nevertheless, the point I wanted to get more is that basically the fact that your memory forensic part, your memory extraction part is working is only because you know how Zeus is working. So it's basically a family
dependent.
Yeah.
You say family. Okay. We tested also the memory forensics also on the Citadel sample, and it worked. But I agree with you that this part can be is not as general as the web page differential analysis. So it's less general. We can say less general. So it can be a weak point if future malware update and change the way they store regular expressions in memory, because the approach to extract the web inject targets is I could say general, but the malware could, for example, try to encrypt also in memory these regular expressions. So I agree with you that this can be could be a weak point.
Okay. That's enough for me.
Okay, thank you. Very, very interesting presentation, very interesting work. Have you considered the fact that some malware types contain active anti-forensic measures, such as trying to detect whether they are in a virtual machine and then changing behavior?
Yeah, we know that we did not focus so much on this problem. I mean, we on the implementation details, our virtual machine have been, I would say, hardened, trying to, for example, we use VirtualBox, and we use some scripts to change the, for example, name of the graphic interface that is also often used by malware to detect if it is running in an emulated system. So we spent some time, but it was not our goals.
However, the sandboxing tool that we use for our sandbox, which is QQ, is very modular. It can permit us to change the virtual engine, and also recently it provides the possibility to use a physical machine as a sandbox.
Okay, and I understand that you have a working prototype, and you are working to get this commercialized, or did I get that right?
Yeah,
on the future side.
It's I'm working on the. I just started a PhD on the same lab when we worked for our thesis, and we have this prototype that is not It's not open to the public, but it's running and active, and we constantly feed it with new malware. Actually, we have developed some crawlers to feed the system with new malwares. And yeah, it is an active prototype, and we think to make it public as soon as possible as a web application.
Other track of question. With regards to the time time you need for the analysis.
Yep.
I mean, envisioning this now in an operational environment. Now, I and my company, I'm setting up a tool like this, want to analyze a set of malware, probably malware files, and putting in. This time is only the analysis time, right? It does not include the time for starting the virtual machine, infecting one of the virtual machines.
Yeah. No. Yeah. This time in the Epsilon axis, you have the total time that includes the time to start the machine, infect the machine with the malware, open the browser, and visit each URL, and download the DOMs, compare the DOMs, and output the signatures, and perform the forensic analysis in parallel. And the label point are the mean time required to process a single URL, because of course the time required is linear with the number of URL processed. So the mean time required to process 68 URLs for a single sample, including the time to start the machines and set up the environment, is about 6-7 minutes.
But this needs to be considered if you go big scale, no? So having a small environment, that's okay. Yeah. But okay, another question for the implementation. How did you automate this testing of these URLs on the different virtual machines? Sorry, I mean, you will have a set of URLs in your, let's say, dirty list or however you want to call it. No, these are 100 URLs I have found or grabbed out and want to check. How do you check now in your system of 10 virtual machines, now with 100 URLs? How did you automatize this process in the virtual machines?
You mean the implementation of the visiting, the downloading the DOM, the URLs in the virtual machines?
Yeah.
Okay.
I mean, you have one virtual machine infected. Yeah. You want to test 100 URLs. Yeah. Let it be like this. No? So, and you want to do it on parallel again with, let's say, 10 other virtual machines which are clean and then making the delta.
Okay.
So how did you do this?
Okay. First of all, the number of virtual machines we used in parallel do the same thing. I mean, if we analyze 100 URLs, each of the 100 URLs is analyzed in each virtual machine, and each virtual machine is downloaded by our server a list of URLs, and automatically sequentially open the browser and visit the URL, dumping its DOM, and then send back the DOMs downloaded. As soon as a new DOM is downloaded, is sent back to the backend server that will process the DOMs as soon as.
Okay, and you have done it with an in sandbox script or something like this?
Yeah.
Okay. Okay, last question from my side. Have you seen any difference in scaling up the number of virtual machines? I mean, I understand you need at least 2, one infected, one uninfected. Yeah. You want to have maybe 3 so that you can kind of see if there's a difference with clean workstations, but have you looked into how many you need or should have?
Okay, we performed some tests to evaluate the number of false differences, so the amount of benign differences that Prometheus wrongly detects as injections. And this, of course, the more virtual machines we use, the less the false difference rate is. And we find that with 10 or 12 virtual machines, we can achieve good performance, that is the 0.7. And so hypothetically, the more virtual machines you have, the best performance you will get. But after 10 or 12 virtual machines, it's like a limit.
Thank you. Okay, the work committee.
Just one quick one. Now, obviously, it might be expensive or difficult for a company to set this up. Have you considered something like a virus total model, where you would perhaps host it and they just give you the URL and perhaps some samples?
Actually, is a web application at which you provide the malware and it returns a web pages with the analysis. However, it is not too costly to install it, because on a simple server you can run all this, because you have only 12 virtual machines.
The actual setup where this system is installed is an Ubuntu machine with 4-core Intel and 24 gigabytes of RAM. And of course, I think that the performance could be improved. For example, adopting like a cloud approach where each virtual machine could be deployed and started in different nodes, but this was not part of our implementation. And so I think that, as my colleague said, it's not so expensive, but we also think to make it public in order to allow companies to upload their sample without installing new software.
Okay, I don't know if we have a question from the audience about. No question. Okay, maybe I can make one, and just to make clear what is for the audience, I can make a question about the audience. So if I get it clear, this is running on the virtual machine, or on a client, or a server?
This is running on a server. When we set up and launch different virtual machine, and inside the virtual machine we run the malware. So this is a server-side component that will produce this signature.
Okay, so I think it's a kind of trend lately, so for the big organizations, because most of the users are just using Word and a browser. So they make virtual machines of that, and they have terminals, like the old time that we used to have that. Yeah, so they have just a screen and a keyboard, and a virtual machine that is running on a server. So yes, this is very economical situation. So your product actually, I hope it will be, could run on this server that has all these virtual machines, because he needs also to have the dump, the memory that this virtual machine is running, yes?
Yes.
And also to have some kind of a clean machines that were all identical.
Yep.
Yes, yes.
Yeah? So that will be a perfect scenario to run.
Yes.
So a big machine, that a big organization has 1,000 employees, he can give them all a virtual machine that is the same, Windows 7, that is clean, and some of them have been infected. So the system administrator needs to show who are infected, who of the virtual machine is infected somehow. Yes?
Yeah, but I think the objective is it's a little different. I mean, we do not want to find out which of the virtual machines are infected. We want to run the malware and extract the behavior, so to generate the signature. And the future objective is to use this signature that Prometheus produced server-side, and use this signature client-side to verify if a machine is infected. So it's like Prometheus, our system is running in a server where companies or automatically crawl new samples and analyze new malware to generate new signatures. And then the client side, the users use the signature generated by Prometheus to verify if they are infected.
But the system admin definitely will find out who is infected. Yes?
Yeah, if
Because normally the users are not capable of doing anything on the machines. But
this is this last part has not already been implemented. The matching of the signature is in our future work. Yeah.
Okay, that's enough for me. Thank you for being here. Okay, I have your caps to remember that you've been to Tallinn. Oh, yeah, this is for you, Andrea. Congratulations. And this is for you, Andrea. Congratulations. Well, actually, I want to thank, first of all, the award committee. I hope you're not on diet. This is for you. Thank you for all the effort. Thank you. Thank you. Thank you. According to the proceeding, the award committee will decide later who will take the first prize and who will take the second. So both of you are winners. Congratulations again. And I want to mention also the review committee, Alexander Weismeier, Christoforos Dadoyan, and Temu Wally Vaisanen. So maybe they see the video and okay. So thank you all for being here. The session actually was to promote this these students to become a PhD students, and also it's definitely commitment of the center to promote master's thesis of the students. So we believe to them that they belong to our academy. So maybe they will also see how good is a conference environment and decide to continue to their PhD. I think 2 of you have already done that. Yes? Yes? Okay. Thank you again for being here.